Welcome back. I want to go through and do an example here of the binomial calculations, and these are the ones that you'll see in the textbook. Not in the textbook, but you'll see other examples similar to this in the textbook. So let's just come up with some sort of thing, a hypothetical situation. First of all, let's assume that you go and you buy a bag of M&Ms. And so you go through and you don't have anything else to do that day, so you count your M&Ms and you see that there are, let's say there's 100 M&Ms in there, in the bag. And you count out that there's 20 of those that are red. Okay, and you're partial to red and you like red, and so the P, we're going to do the estimate of P for that is going to be 0.20, or 20%. Now, obviously, the next time you go and buy a bag of M&Ms and open it up and count the number of reds in there, you may not get 20%. That's just what you got out of that one bag. That's a sample of the entire population of M&Ms. And so now you've got your 0.20. So, from this information, we can go through and we can calculate a confidence interval on how many red M&Ms you would expect in the next bag, assuming that they're drawn from the same population. So Q is going to be 0.8, which is 1 minus the 20. Of course, N is equal to 100. So let's go through and calculate the mean. Sometimes you're going to see the mean as expected value of X. We know that for the binomial, that's NP, which is N is 100 and P is 0.2. So that's going to be 20. Obviously, the expected number that you're going to get from that. And then let's calculate the variance. And we know that is going to be NPQ. So it's going to be 100 times 0.2 times 0.8 is going to give us 16. And from that, we can calculate the standard deviation is going to be 4. Now, if we want to construct, given this information, if we want to construct a 95% confidence interval, then that is going to be, the lower limit is going to be the mean, 20, minus 1.96 times the standard deviation. Okay, now a lot of times this number 1.96 will just be rounded off to 2. So let's just, to make the calculations a little bit easier, we'll just go ahead and do that at this point. There's not much difference between the 196 and the 2 statistically. So that means that a lower confidence interval is going to be 12. And rounding it off to 2 in this situation makes sense because, this is a whole number and you're going to end up with 12 M&Ms instead of 12 point some odd number. That's the lower confidence interval. So the upper confidence interval is going to be 20 plus 2 times 4. That's going to be 28. Now, what does that tell you? That tells you that the next bag of M&Ms that you get, you should be 95% confident, 95% sure that you're going to get somewhere between 12 and 28 red M&Ms out of a bag of 100. Or since we used 100, then you're going to expect to get 12% to 28% of those would be red M&Ms. Now, it's important for us to go through and to truly understand what the confidence interval means to us. This is based on a confidence interval of 90%. It's a little bit easier to work with. It only has 10 lines here. So you see that the 90% is here. Then we have 10 samples. This is the true mean, the population mean. When we worked with the M&M example, we don't know whether the true population mean out there is 21 or 22 or 19%. It was just 20% in our sample. And so that's the true population mean. We might have gotten a sample that's off to the side like this, where our mean is sort of in the middle, but the true population mean is there. The important thing is that our confidence interval contains that value. Now, if you go down through this, you see that there's this one sample right here that is outside, that doesn't contain the population mean. It's at the 90% level, and that's what we expect. At the 90% level, we expect 90% of our confidence intervals that we construct to contain the true population mean. The challenging thing about that is that we do not know. We might get this sample and we might think that it's a good sample, but it doesn't contain the true population mean. There's still that 10% chance of not knowing, or of uncertainty. So we don't know if this sample is a better sample than that sample. And that's one of the reasons why you'll hear us as statisticians keep talking about randomization and the importance of going through and randomizing your results. Before we end this one up, let's just go back and hit this. These are the common values for the z-score distribution. You're going to see these over and over and over again. I want you to memorize them. 90%, it's at 1.645. 95%, 1.96. 99%, it's 2.575. And this is the one that we just used, and we rounded it off to 2, just to make it a little bit easier for ourselves. And what we find out is that, you'll see it in the literature and in this information in the book, that that's called the maximum usual or the maximum or the minimal usual values. Can't talk today. Is 2 standard deviations above or below the mean. Again, that comes from that 1.95 being rounded up to a 2. So we're going to come back in just a minute and do another one of these. So hang on and we'll be right back.